طلبة وطالبات الصف الثالث الثانوي القسم العلمي رياضيات لغات، أهلا بيكم في حلقة جديدة من حلقات برنامجنا برنامج كالكولس. النهاردة إن شاء الله هنستكمل مع بعض موضوع behavior of a function. اتكلمنا قبل كده عن increasing و decreasing بتوع الفانكشن، اتكلمنا عن اللوكال ماكسيمم واللوكال مينيمم، اتكلمنا عن الكريتيكال بوينت، واتكلمنا عن الابسوليوت ماكسيمم والابسوليوت مينيمم. تعالوا النهارده نستكمل الموضوع ونتكلم عن convexity of a function. ازاي الكيرف يبقى convex upward او convex downward. كمان نتكلم عن inflection point. وجد convex up و convex down ورا بعض يبقى اكيد في inflection point هنتعرف عليها النهارده. كمان نقدر النهارده نرسم اي كيرف او ندرس اي كيرف مرسوم لو هو مرسوم، او لو عرفت البروبرتيز بتاعته ازاي اقدر ارسمه او ادرسه واعرف يا ترى لو عندي اكتر من رسمه اعرف انهي رسمه اللي هي تعبر عن الكيرف اللي انا بتناقش معاكم عليه. Dear students of grade 3 secondary, welcome to our maths program. Today we have calculus. Our lesson today is convexity of a function. Convexity and inflection points sketching. Let's start with the definition. Let f be a differentiable function on the interval open interval a and b. The curve of the function is convex downward if f dash is increasing on this interval and convex upwards if f dash x is decreasing on these intervals. What a meaning of f dash increasing and f dash is decreasing? F dash is increasing, then the slope of f dash is positive. The slope of f dash means the second derivative of the function f, or f double dash x. Then we can discuss a very important theorem. If the function f of x is a function for which f double dash x smaller than 0, smaller than 0 means negative value, over an interval, then the graph of the function f of x is convex upwards over this interval. So, if the sign of f double dash x is negative, then the curve is convex upward in this interval. What about f double dash positive? Then the curve is convex downward. Now, point of inflection. A point of inflection of a curve is a point where the curve changes from convex downwards to convex upwards, or vice versa. We have a curve of a function. The curve is convex upwards and the curve changes its direction and the convex now downwards. The point between the two branches of this curve called a point of inflection. Let's start with the first example. Determine the intervals over which the curve of the following function is convex upwards or convex downwards, and the points of inflection if any exists. The function f of x equals x to the power 3 minus 9x to the power 2 plus 24x minus 4. To discuss the convexity of a function, we find the second derivative of this function. Let's start with the first derivative. F dash x equals 3x power 2 minus 18x plus 24. The second derivative, f dash x equals 6x minus 18. Now, put the second derivative, f double dash x equals 0. So, 6x minus 18 equals 0. And 6x equals 18 divided both sides by 6. Then the value of x equals 3. We have two intervals. The first intervals the first interval from negative infinity to 3, f double dash of 2 equals 6 multiply 2 minus 18. 12 minus 18 equals negative 6. Then the sign of f double dash in this interval equals negative 6, negative value smaller than 0. Then the function is convex upward in this interval. So the curve of the function is convex upward in the open interval, negative infinity and 3. Now, in the open interval, 3 and infinity, f double dash 4 equals 6 multiply 4 minus 8. 6 multiply 4 equals 24, minus 18 equals 6. 6 bigger than 0. So the sign of f double dash x in the open interval 3 and infinity is positive. And the curve of the function this interval is convex downwards. We have in this case an inflection point at x equals 3. What is the corresponding value of x equals 3? What is the value of y? To get the y, we must substitute in the original function. F of x or f of 3 equals 3 power 3 minus 9 multiply 3 power 2 plus 24 multiply 3 minus 4. Then f of 3 equals 14, and the point 3 and 14 is an inflection point, or the point 3 and 14 is a point of inflection. Another example. The curve of the function f, where f of x equals between two brackets x minus 2 multiply e to the power x, is convex upwards in the interval negative and 2, open interval negative 1 and 2, open interval negative infinity and 0, open interval 0 and infinity, or open interval 0 and 2. We have function f of x equals product of two functions, x minus 2 multiply e to the power x, x minus 2 polynomial function, e power x exponential function. The product of the two functions, x minus 2 times e power x, is the rule of the function f of x. Now, the first derivative f dash x equals the derivative of the bracket x minus 2, the derivative of this bracket equals 1 multiply e power x plus the bracket x minus 2 multiply the derivative of e power x, which is e to the power x. Now, the second derivative, f double dash x equals the first term e power x, the derivative of e power x is e power x plus, what about the derivative of the product of x minus 2 multiply e power x? The derivative of this term is e power x plus x minus 2 between two brackets multiply e to the power x. Then f dash x equals e power x plus e power x equals 2 e power x plus between two brackets x minus 2 times e to the power x. Now put f double dash x equal 0. Then 2 e power x plus between two brackets x minus 2 times e power x equals 0. And we can take e power x as a common factor. E power x multiply between two brackets 2 plus x minus 2. Then x multiply e power x equal 0. Then the value of x equals 0, and we know that e power x doesn't equal 0 because any exponential function or the exponential function e power x thrown above x-axis, so e to the power x not equal 0. Now, the number line, we have two intervals. The first interval, open interval, negative infinity and 0, f double dash of negative 1, any number belongs to this interval. The value of f double dash negative 1 equals e multiply e power negative 1 plus negative 1 minus 2 between two brackets multiply e power negative 2 equals e power negative 2 e power negative 1 minus 3 e power negative 1, which equals negative e to the power negative 1, or negative 1 over e. Negative e power negative 1 equals negative value smaller than 0. So the sign of f double dash x in the open interval negative infinity and 0 is negative. And the curve of the function in this case is convex upward. What about the open interval 0 and infinity? F double dash 1 equals 2 e power 1 plus 1 minus 2 multiply e power 1 equals 2e minus e, which equals e. E is number, is a positive real number bigger than 0. So the curve of the function in the open interval 0 and infinity is convex downwards. The curve of the function changes its convexity from upwards to downwards, then we have an inflection point. And the required is the curve is convex upward in the interval, open interval, negative infinity and 0, and we can choose letter B. Another example. If the function f, where f of x equals between two brackets 2x minus a all to the power 3 plus 4 has an inflection point at x equals 5, then the value of a equals 2, equals 4, equals 5, or equals 10. We have a function f of x equals, and this curve has an inflection point. Then the second derivative of this function at x equals 5 must be equals 0. Now the function f of x equals 2x minus e to the power 3 plus 4, and the first derivative of this function is f dash x equals the derivative of the bracket 2x minus a all to the power 3 is 3 multiply 2x minus a all to the power 2 multiply the derivative of the function in the bracket, which is the derivative of 2x minus a, which is 2. So f dash x equals 6 multiply 3x minus a all to the power 2. What about the second derivative? The second derivative, f double dash x equals 2 multiply 6, which is 12, multiply 2x minus a, multiply 2. Or f double dash x equals 24, multiply between 2x minus a. Now, the curve has an inflection point at x equals 5. Then, f double dash x equals 0 when x equals 5, or f double dash 5 equals 0. 24 multiply between two brackets 2x minus a, x equals 5, so 24 times between two brackets 2 times 5 minus a equals 0. We get 10 minus a equals 0 and a equals 10. Dear student, another example. Sketch the curve of the function f, where f of x equals x power 3 minus 3x plus 2. First, we have a polynomial function f of x equals x power 3 minus 3x plus 2. F dash x equals, the first derivative of x power 3 is 3x power 2 minus the derivative of 3x is 3. And 2 is a constant, the derivative of the constant equals 0. So f dash x equals 3x power 2 minus 3. What about the second derivative? F double dash x equals 6x, the derivative of 3x is 6x, and the derivative of negative 3 is 0. Now put f dash x equals 0 to get the critical point. Then 3x power 2 minus 3 equals 0. Divide by 3. X power 2 minus 1 equals 0. We can factorize the left-hand side as a product of two factors. The first bracket x minus 1 multiply the second bracket x plus 1 equals 0, and x equals 1 or x equals negative 1. We can discuss the behavior of the function in the interval negative infinity and negative 1. The sign of f dash x is positive and the function f of x is increasing. In the open interval negative 1 and 1, the sign of f dash x is negative and the function is decreasing. And the third interval from x equal 1 to x equals infinity, the sign of f dash x is positive and the function is increasing in this interval. And the y value of x equal negative 1 or the corresponding value of x equal negative 1 is 4, and the corresponding value of the x equal 1 equals 50. Now in the open interval negative infinity and negative 1, f dash negative 2 equals 9. 9 is a positive value, so the function is increasing. This is in this interval. And in the open interval negative infinity 1, f dash 0 equals negative 3. Negative 3 is smaller than 0, and the function in this interval is decreasing. What about the third interval? From 1 to infinity, f dash 2 equals 9. 9 is a positive value, so the function is increasing in this interval. At x equals negative 1, it is a point of local maximum value because the curve is increasing in the left of this number and decreasing on the right of x equal negative 1. The corresponding value, f of negative 1, equals 4. So the point negative 1 and 4 is a critical point and is a point of local maximum value. And the maximum value equals 4. Now at x equal 1 is a point of local minimum value because the curve of the function decreasing in the left of x equal 1 and increasing on the right of x equal 1. So the point 1 and 0 is a local minimum value and the critical point. 1 and 0 is a critical point and is a point of local minimum value. Now, to discuss the convexity of the curve, put f double dash x equals 0, then 6x equals 0, and the value of x equal 0. We can discuss the relation between the sign of f double dash x and the behavior of the curve f of x. In the open interval negative infinity and 0, f double dash x negative and the curve is convex upward. And in the open interval 0 and infinity, the sign of f double dash x positive and the curve is convex downward. In this case, we have an inflection point at x equals 0. When x equals 0, the value of y of f of x equals 2. So the point 0 and 2 is an inflection point. In the open interval negative infinity and 0, f double dash negative 1 equals negative 6. Negative 6 smaller than 0. So the curve is upward. in the open interval 0 and infinity f double dash 1 equals 6, 6 bigger than 0 or positive. So the curve of the function is convex downward in this interval. And the point 0 and 2 is an inflection point. We can draw the curve of this function by using the following table. When x equals negative 2, y equals 0. When x equals negative 1, y equals 4. X equals 0, y equals 2. When x equals 0, and when x equals 1, y equals 0. And when x equals 2, y equals 4. The points negative 1 and 4, 1 and 0 is a critical point, and negative 1 and 4 is location of local maximum. 1 and 0 critical and location of local minimum. What about 0 and 2? 0 and 2 is point of inflection. So we can use the table to draw this function. The function is increasing in the open interval negative infinity and the negative 1. The curve of the function is decreasing from negative 1 to 2 and increasing in the open interval 1 and infinity. The point negative 1 and 4 is a local maximum point and the critical point. The point 1 and 0 is local minimum value or local minimum point and critical point. The curve is convex upward in the open interval negative infinity and 0. The curve convex downward in the open interval 0 and infinity, and the point 0 and 2 is an inflection point. So the curve of the function f of x is drawn by these properties of the function or the behavior of the function. Another example, sketch the curve of the continuous function f which has given properties. F of 4 equals 2, f of 3 equals 4, f of 2 equals 0. Now, f dash x smaller than 0 for x smaller than 2 or x bigger than 4. F double dash x positive, bigger than 0, positive, when x smaller than 3. And f double dash x negative when x bigger than 3. Now we have f of 4 equals 4. Then the curve of the function passes through the point 4 and 4. 2 f of 3 equals 4, divided both sides by 2, then f of 3 equals 2, and the curve of the function passes through the point 3 and 2. We have f of 2 equals 0, that means the curve passes through the point 2 and 0. Then the curve of the function passes through 3 given points. Now what about the increasing and decreasing? F dash x smaller than 0 is a negative value when x is smaller than 2. So the curve in this case is decreasing, or the function is decreasing in the open interval negative infinity and 2. F dash x positive when x bigger than 2, smaller than 4. So the function f of x is decreasing, is increasing because f dash positive in this interval, in the open interval 2 and 4. At the last case, f dash x smaller than 0 means f dash x is negative when x bigger than 4. When f dash x is negative, so the function of this function is, the curve of this function is decreasing in this interval or in the open interval 4 and infinity. Now we have f dash x negative in the open interval negative infinity and 2, so the function is decreasing in this interval. F dash x positive in the open interval 2 to 4, then the curve of the function is increasing in this interval. F dash x negative in the open interval 4 and infinity, so the curve of the function decreasing in this interval. At x equal 2, f dash x equals 0, so we have a critical point at x equals 2. What about x equals 4? When x equals 4, f dash x equals 0, then we have another critical point at x equals 4. At x equal 2, we have local minimum value because the curve of the function is decreasing in the left of x equal 2 and increasing at the right of x equal 2. What about x equal 4? At x equal 4, the function has local maximum value because f dash positive, or the function increasing at the left and decreasing at the right. What about f double dash x? F double dash x negative when x is smaller than 3. So the curve of the function is convex upward in the open interval negative infinity and 3. And f double dash x positive when x bigger than 3. F double dash x positive, then the curve of the function is convex downward in the open interval 3 and infinity. Now we have open interval negative infinity and 3, f double dash x negative, and the curve is convex upward in this interval. In the second interval from 3 to infinity, f double dash x positive, and the curve is convex downward. In this case, we have an inflection point because the curve changes its behavior from convex upward to convex downward at x equals 3. So we have an inflection point at x equals 3. We can draw the curve of this function as the curve is decreasing from negative infinity to 2, increasing from 2 to 4, and decreasing from 4 to infinity. The curve convex downward in the open interval negative infinity and 3, convex upward in the open interval 3 and infinity. The curve has local minimum at 2 at the point 2 and 0, local maximum at 4 and 4, and the curve has an inflection point at the point 3 and